Today's essential question is, how can you determine the continuity of a function and identify any vertical asymptotes? This video is going to deal specifically with continuity, and in another video I'll deal with the idea of a vertical asymptote. Function continuity fits into four different categories. The first is the most simple and easiest to see, and that is this graph is just going along, and we can draw the whole graph in one continuous motion without ever having to pick up our pencil. And so we say this function is continuous for all x, or continuous for all x in the domain. This second example kind of looks continuous. This graph is going along, but you hit this hole here in the graph. And on the other side of the hole, the graph just picks up where it left off and just kind of keeps going. So it's not continuous. We can't draw this graph without picking up our pencil. But it's almost continuous with the exception of that one tiny little dot, that hole that's missing. And there may or may not be this point that's defined somewhere else at x equals a. That may be there, that may not be there, but that's not the point. The point is that there is a hole along the graph. And so that hole there, we say that this function has a removable discontinuity at the point x equals a. So at x equals a, there's a removable discontinuity. It's removable because if we could put a point right in that hole, we would remove the discontinuity and the function would be continuous. So that's where the name removable comes from. The third example here is a little bit like a removable discontinuity. We're going along, and then we hit this break in the graph, and we have to stop, pick up our pencil, and this graph starts at a different location over here and keeps going. And that different location is what makes this different than a removable discontinuity. There's this big sort of gap in between the two pieces of the function. There's a big jump, and that's where we get this name. We say this function has a jump discontinuity at x equals a. So we identify the type of discontinuity it is and give the location at x equals a. We can't plug in that gap. We can't connect the two parts of the function with just one single point. And that's the difference between a jump discontinuity and a removable discontinuity. And the fourth and the last example here is our function is going along, and then it takes this sharp bend upward or downward in a different example. And then there's another gap, there's another break, and the function picks up over on another side here and keeps going. And what you might not see is there's actually sort of a invisible vertical line there. This vertical line would be the equation x equals a, and we'll talk more about exactly what that line is in another video, which you might guess based on today's essential question. But the idea here is on the left side, this function bends upwards and keeps going upwards forever towards infinity, getting closer and closer and closer to a on the left side. And this piece of the graph goes downward forever and ever and ever, getting closer and closer to a from the right side of this graph. And it's that up forever and down forever that gives this function an infinite discontinuity at x equals a. So your function is either continuous or it's discontinuous. And the discontinuities can be classified as either removable, jump, or infinite. Let's look at this equation f of x equals 1 divided by the quantity 1 minus x. Is x equals 1 a point of discontinuity? We can simply substitute 1 in for x. Do 1 over 1 minus 1 and get 1 over 0. When 0 is in our denominator, this is an undefined value. And that undefined tells us the answer is yes, x equals 1 is a point of discontinuity. Because the function is undefined at x equals 1. That's a type of discontinuity. Now, what type of discontinuity is it? We're going to have to look at the equation or look at the graph for right now to figure out what type of discontinuity it is. So take your graphing calculator, go to your y equals, and we're going to put in 1 divided by 1 minus x. Make sure we put parentheses in our calculator around the denominator 1 minus x. Once your equation is in there, we're going to do a zoom 6 to get a standard viewing window. And the graph should look something like this, and you should hopefully be able to see, if I can draw it in there carefully enough, something like a dotted vertical line kind of right in between those two pieces. And that should then indicate that the discontinuity at x equals 1 is an infinite discontinuity. And what we're going to see the more that we do this is when the denominator equals 0, often, but not always, usually that leads to an infinite discontinuity. It's when that denominator equals 0. Here's another function we want to test to see if x equals 1 is a point of discontinuity. Let's do the same thing we did before, and that is plug 1 in to the function. We're going to get 1 squared minus 1 in the numerator, 1 minus 1 in the denominator. We're going to get 0 over 0. With the 0 in the denominator, we know that this function is going to be undefined when x is 1. So automatically we know, based on our last example, yes, this is a point of discontinuity. Yes. X equals 1 is a point of discontinuity. Okay? The question is, what type of discontinuity is it? Now, when we put 1 in for x, we can see that the denominator here equaled 0. It's tempting, like in the last example, to say, well, it must be an infinite discontinuity. But remember, I said denominators equaling 0 are usually infinite discontinuities, but not always. So let's look at the graph to figure out what type of discontinuity it is. In your y equals, make sure you put both your numerator, since it's got 2 terms, and your denominator, since it has 2 terms, in parentheses in your calculator. Once you've got your equation in with parentheses around your numerator and denominator, again, we're going to do a zoom 6 to view this. And the result looks like a straight line. It looks continuous. Now we said, specifically we're looking at x equals 1, which is something like right here. We said, though, already that there is a discontinuity at x equals 1. We figured it out by plugging in. So what type of a discontinuity looks continuous? Was that very first example that we did where it looks continuous. Let's take a look at the table of values, so second graph in our calculator, to see kind of what's going on near x equals 1. A quick look at the table, and we see that there is in fact an error at x equals 1, just as we suspected, and that's the discontinuity. But look at the y values, -2, -1, 0, skip 1, 2, 3, 4. It looks like this function is completely continuous, just missing that y equals 1 that should be kind of right here if we were to see a continuous function, -2, -1, 0, 1, 2, 3, 4. So what is this? This is an example of a removable discontinuity at x equals 1. And you can see it on the graph. We didn't really see it in our function right away when we plugged values in, but I'll show you how we can see that algebraically. If we factor the numerator, we can take an x out. When we factor the x out of the numerator, we're left with x minus 1. But that is also our denominator, x minus 1. And anytime you have a common factor in your numerator that cancels out a common factor in the denominator, you no longer have the denominator equaling x minus 1 after you've done the canceling out. And therefore, x equals 1 is not a vertical asymptote or a infinite discontinuity like we saw earlier. It results in a removable discontinuity, and that's when the denominator cancels with a factor in the numerator. Now the last example of a jump discontinuity is a little bit harder to illustrate, so we're going to save that one for a little bit later, but here was an example of removable. You can't really see it on the graph unless you look at the table and look for the error right here, and the infinite discontinuity where you see that sort of vertical dotted line show up. So these are your three types of discontinuities, and the fourth example being continuous, where we can draw our function without ever picking up our pencil.